Hey, look what came in the mail! Some Raspberry Pi Picos. Yeah, let's take a look at them using my new microscope, and then we'll try hooking them up to a computer. I'm using my add-on star AD207 microscope to look at these. And I lost the comprehensive instructions sheet, so I was SOL. I could not find it anywhere on the internet, which is lame. So hopefully it's recording video. Oh, I can be just like that one guy in New York. All right, USB, looks like it's using USB micro. Well, I prefer USB mini, but you know me. I am the USB Luddite. All right, looks like we have protection diode. This is probably going to be your regulator. I think this thing uses 2 voltages, 3.3 for the I/O and 1.8 for the internal circuitry, or the core. Boot select. So the chip itself has 16K of ROM, which is used as the bootloader. So basically, it's unbrickable. Kind of reminds me of the parallax propeller. Kind of funny. And that's going to be your quad spy flash. So reading the data sheets, there doesn't appear to actually be any flash or appreciable amount of flash on the chip itself. It loads a program from this external EEPROM, so that would be execute in place, so to speak. That's kind of what the like the ESP8266 does. And this is, well, since it's Cortex M0 base, that's probably going to be a 32767 kilohertz oscillator there. Pi logo, debug. Let's see, ground, and then probably SWD interface, so clock data. Yeah, that goes into the chip and nothing else. I like how it's got castellation here, so you could actually solder this in a surface mount style onto a separate motherboard. Yeah, it's pretty simple. So basically, if you turn on the system while holding this, no matter what you've done to it, you'll get the it'll come up as a mass storage device, and then you can drag and drop what is it, UF2 files onto it. That's a pretty common thing for microcontrollers these days. Oh, it's all nicely labeled. Look at that. Analog ground, general purpose input output 27A0. Oh, a run pin. Oh, that's great. Oh, a little QR code. Oh yeah, there you go. Yeah, SWD I/O and SWD clock. So yeah, that's your standard ARM microcontroller programming interface. Oh, those are test points for the USB, I wonder? Probably. Well, okay, so I guess the idea is the Raspberry Pi Foundation made their own silicone and had someone manufactured, obviously, because before it was basically a Broadcom, multimedia processor that was the heart of the Pi. Yeah, so this is going to be like a Cortex M0 ARM, very common low-cost microcontroller, except for this one has a lot more RAM than those usually do, and then it has 2 cores, and then the speed is also higher. So yeah, let's look at what it takes to get this fired up on a computer. So I got this document, Getting Started with the Raspberry Pi Pico. Of course, I'm interested in C, C++. So there's also some videos on YouTube that I watched. But oh man, there was a lot of steps to get this up and running with Visual Studio Code on Windows, which is what I wanted to use. I don't really like this hipster stuff where it's like, oh, here's how to do it in Linux, and then Mac. And then Windows, like Windows is an afterthought. Hello, Windows has the most of the market. I know a lot of tech geeks, use Linux, but I don't want to spin up a Linux box or use my Linux box to do this when I can do all my other development on this PC. Well, anyway, so on Windows, you have to install the ARM GCC compiler, which I don't think I had that already because, normally I just use AVR Studio. CMake, and then I had to add some tools for Visual Studio 2019, which works with Visual Code, Python 3, which I had to update, and Git. And normally I just use the desktop version of Git because it's 2021, and I don't want to type everything in like some sort of caveman from the 70s. There was a lot of steps that you had to do, and a bunch of things you had to add to the path. And even then, I have it here in Visual Code. I actually used Visual Code when I was doing that Big Tree Tech SKR 1.3 project. So using some examples online,
Yeah, I have this. And it looks like it's missing this library. So even like with this, you actually have to go and you have to do you have to load a developer command prompt. But you have to run code from that in order to have the right environment for it to work correctly, even after you set everything up. All right, so let's see if this builds. Now, the reason this seems a little weird to me is I was using Visual Studio Code, like I said, when I was doing that custom printer I built last spring. I never made a video about it, but I talked about it in some videos. And so I got the Marlin fork, and that was using, I think it was like using like a Nordic. It's either Nordic or NX. No, it was NXP. Yeah, it was an NXP ARM M4, I want to say. And it was pretty easy to set up in this code. I mean, I just had to add a few modules like Platform IO, and it basically just worked. And this is the same thing. This is like a Cortex M0, and oh man, it was just so much more difficult. So yeah, I've got the pin blinking. That's great.
I also don't really like this. You have to hold down boot, then power it up, then release boot, and now it comes up.
So even after you compile it, you have to go into the folder, go into build. There it is, tester UF2. So, okay, there's the mass storage device. So we drag that over, and then it will program it, and then the code will execute and start blinking.
And now, after all that work, we finally have a blinking light. So, you know what? Yes, I am not that good at programming in computers. No matter what you think, there are millions of people better at it than me. Still, I have a lot of experience using different programs, and this just seemed really obtuse and complicated. It kind of feels like this thing is really meant for MicroPython, which I guess I'll try next. But before I do that, I'm going to see how fast I can get this to run. So let's just remove the sleep and spit it out as fast as possible. Rebuild. And yeah, even here, I can't just tap the button. I have to hold down the button, physically unplug it, plug it back in. So that's not as easy as like how the Teensy works.
Yeah, I mean, it works. It seems like there's a lot of steps. And, you compare that to the Raspberry Pi, the normal one, where you make an image on an SD card and it basically just works. Or, the Arduino IDE is a bloated mess, but, you hook it up and it just works. This was a lot of steps. I'm going to see how fast I can get the LED to blink, and then I'm probably going to try MicroPython next.
Okay, I changed it to pin 16, not the LED. Let's see what we got here. 10 megahertz. No, is this only... Wait, I thought the pins were 3.3 volts. What's the scale? 5 volts. 1 volt. Do I not have a good ground reference? Why is that floating like that? 31 megahertz? Oh, that's pretty good. Yeah. So why is the voltage floating like that? That's weird. Let's try that. That's odd. It might be faster than the scope can detect. Let me try slowing it down. Okay, I slowed it down to 10 microseconds. Yeah, now you can see the total voltage of, it's like 3.6. Yeah, so the reason you didn't see the total rise and fall is because it was rising and falling faster than this 70 megahertz oscilloscope could detect. Although we could still see the peaks, which means, we knew what the frequency was. So I think what I'm going to try next, because I think that's what this is really intended for, is to put MicroPython on it. And since Python, it's an interpreted language, what I believe we can do is we can just put the image onto it, and then I believe it also uses its own flash as a storage system. So instead of having to, program this, reprogram the flash every time, you're basically programming on the chip.
Okay, Raspberry Pi Pico. All right, so getting started with C++ is pretty labyrinthian. If you want to do it, you can Google it. I'm not going to show you all the steps because it would bore you to death. It bored me to death. MicroPython, though, you just download one file and you slap it onto the Pi, and then you can program everything over the command line. So it's like a little mini computer, basically. Okay, print. What is it? Hello world. Okay, that's great. So how do we Yeah, so it's like, what do they call this? The REPL, read, evaluate, print loop, which, you know, is a fancy way of making you think it's not like BASIC, even though it's very much like BASIC. Yeah, so I'm going to see if I can find some example code to toggle the I/O, and we'll see how much slower it is. It's certainly not going to be faster. All right, I downloaded this program called Thani. It was recommended by Raspberry Pi, and I've selected the MicroPython Raspberry Pi Pico as the interpreter, and then the port, and it looks like I'm connected. So let's see, this would be the immediate mode. Hello. Okay, so up here, I guess we could type a program. Yeah, so let's send this over. There's no delay, so we're going to see how fast it can possibly toggle the port. I changed it to 16 because that's the pin that's hooked up to the oscilloscope. Okay, there it is. This one is about 56 kilohertz. So it's, I think the word I would use is infinitesimally slower. Well, it's an interpreted language. It's, you know, it's kind of like BASIC. There's tokens, and it's like, oh, look, you know, we're going to interpret this language as we load it. So you don't have to compile it. It just runs. And, I think nowadays, since computers are so fast, I mean, if BASIC ran this fast back in the day, people would be doing backflips. And so we use the high speed of our computers to make up for the fact that, you know, an interpreted language like Python isn't going to run nearly as quickly as assembly. But it does seem like this is a much easier way of doing it, because I just, you know, flashed over one image, which I can just leave on it. You know, I can just leave that image on this permanently. I flashed that over, and then with one little program that I downloaded, it just worked. So it is definitely much easier to program this in MicroPython than C++. At least on Windows. I'm sure it's easier on Linux. Well, since apparently I can't bore you looking at data sheets, I'm going to look at some more data sheets. I guess people like this for some reason. I don't know. Here's the memory map of the Raspberry Pi Pico. And so we see we have ROM base, that's what it boots from. Then we have zip, which is execute in place. And that is, that's how it's executing the code from that external flash. So it's mapping that external flash to its own address space. And then we see we have the SRAM base above that. So we have that in hex. So what is that? Hex. Well, that's quite a large number. Wow, it maps it that high. Well, I guess that makes sense. It's a 32-bit processor, so its address range is going to be, you know, 4 gigabytes. Yeah. So if they're mapping the RAM that high, that means you have a pretty wide range of external flash you can attach to it. You know, I don't know, this data sheet, I also, I'm being kind of negative, but I don't really like the way it's written. It's not really written the same way as most microcontroller data sheets are. I mean, because, you know, you could look at something from like STM or Nordic or Freescale, Atmel, Microchip, and, you know, they all pretty much follow the same pattern, but this one's kind of different. I guess, can I jump to it? Okay, cool. Well, I think what I'd like to do next is just talk about some other alternatives and why I don't think... Well, I've seen people online saying, oh, this is the Arduino killer. And really, this... I mean, obviously, this is leagues beyond an Arduino, like a little simple IT Mega. It's more like an ESP8266. However, those are also really cheap, but you get Wi-Fi. Yeah, just for an example, let's look at a SAM D51 that I have. Oh, I'm going to get in trouble now. I'm looking at DigiKey. All right, so SAM D51, let's see, RAM size, lots of RAM, program memory size, 512K, that's pretty good. How many do we get? 0, oh yeah, it's 192 by 8, okay. Yeah, okay, so this is going to be like what, like the Adafruit Metro M4 uses. I'm just going to click on a random one here. Yeah, so, well, it is definitely more money, like the chip itself, well, just one of them's $5.70. But, you know, you get into mass quantities and you start to get down there. I'm sure Adafruit gets them for pennies. But this is based off M4, right? So it's going to just clean the floor with a Cortex M0. It just has so much more stuff under the hood. The SAM D5 family data sheet. So we're running at 120 megahertz. It's a single core. So yeah, it's obviously it's not as good as a dual core, but the chip itself is pretty beefy. You have all sorts of stuff. You can have up to 1 megabyte of flash, up to 256 K of SRAM. There's additional RAM. It also has dedicated buffers for the SDHC SD card driver. Yeah, 32 channels of direct memory access. That's a lot. Two SDHC memory card interfaces, 4-bit each. Pretty much runs at full speed, 5 megahertz. It also has execute in place support, so you could attach even more external storage to this to execute code from. Ethernet controller, CAN bus. That's what they use in cars. That's how your airbag knows that your engine blew up. It's got crypto. It's got a CRC32 generator that can actually work in tandem with the DMA. True random number generator. It uses ADCs inside the unit. Yeah, it's pretty powerful chip. And yes, it's more than $4, but it's pretty powerful. It even has I think they talked about like the Raspberry Pi Zero has that what they call it, like the logic. Well, they have that here too. They call it configurable custom logic. So you can basically create a bunch of state tables, so some of your pins can act like gates, which actually is, somewhat useful. That means you could avoid having like an external AND gate or a NOT gate, because sometimes you do need that even in this modern age.
You know what? I'm determined to build something with this. So I'm going to breadboard it up just like Ben Eater, because everyone named Ben is super cool. Man, if my name was Ben Eater, I would like make like a theme song like from Metal Gear. It'd be like, I'm still in a dream, Ben Eater. Blah, 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 blah. Someday you make a computer, bow, bow, bow. Someday you make a 4-bit timer, bow, bow, bow. And the day... Too stupid. So I have this. This is something I've been working on. It's a cat laser module. I was going to do it with ESP8266. Probably still will, but I think it might be a good example for this. I'm sure I can find some servo code for Python. Yeah, so it's got 2 lasers. So I noticed there's a V-bus pin on this, which is probably going to be 5 volts off the USB. That should be enough. So I use a couple transistors. That way I'm not directly driving the lasers with the I/O.
Actually, we can probably do the lasers first. Let's call it laser 0. And what is that? 14, 15 for the pins. Yeah, we'll just toggle those for now. Yeah, I've just got a 4401. What's it called? Oh yeah, transistor hooked up to it. So we'll see if that works. U time sleep. I'm assuming this is milliseconds. I could just type it again, but I'm lazy. Programming's all about being lazy. Did that work?
Make like a forward and focus. Found the right timer module. Oh, there we go. Okay, there's the blinking lights. So yeah, we have control over both of them, I guess. All right, cool. I'm gonna merge in the PWM example. We'll hook up that up to the scope and see if we can get these servos moving too. Then I'll need to find a random number generator. Oh, I've got like...
All right, let's look at the PWM example. Import time. Okay, we have that from machine import pin and PWM. Oh, this is the part where I should tell you I don't know anything about Python. It's like a snake. Yeah, let's see if... Actually, let's see if that works. Yeah, okay, that works. Okay, so we were able to get pin and PWM from the machine. I assume that's a library. Yeah, let's see if I can stumble through this. All right, def, laser, cats, colon. All right, so then here we'll just do laser. Laser cats! In the future, there was a nuclear war. And because of all the radiation... Oh, laser cats. Oh, do I have to define it before I do it? Okay, there we go. Oh, okay. So it is kind of like C in that case where you have to define it before you do it. Very well. How do you actually turn the pins on or off? I'm going to go back to the documentation for that because I don't really like toggling pins. I've never liked that. Oh man, I feel like a babe in the woods. Not the pig. All right, so I created a variable a, then Waltrue lasercats pass a equals a plus 1. So over here we turn a into state, then we do state equals state and 1, which basically toggles it. Well, no, it doesn't toggle it. It removes everything but the LSB. Okay, so imported pin and PWM. So PWM equals, okay, so we can take that. So we're going to use pins 16, 17 for the two servos. And I guess I can call it X servo, Y servo. Okay, set the PWM frequency. Okay, so in this case, we're going to want it to be 50 hertz. All right, so PWM duty U16, I guess that means it's a 16-bit number. I'm kind of curious what the granularity of that is. Everyone's probably like, oh man, he's just copy pasting. It's like, yup. Oh, I see. Yes, I'm okay. Remember what I said I didn't know anything about Python? There we go on the scope. Again, I don't know what the granularity of this is. Frequency 50 hertz. Okay, that's what we want. So servo is 1 millisecond to 1.5 milliseconds, I want to say. And this is what I set it at. 500? What is that? 500 watts. Oh, well, it's a duty cycle, so I'm going to have to look into that to figure out what number to use. But once I figure out what number to use, then I can scale it to be 1 millisecond minimum pulse width at 50 hertz, and then it should drive a servo. I wonder, 16-bit number. The example says duty times duty, and duty goes up to 255, so...
Oh, here's something interesting, but probably should be obvious. If I actually stop the program, the LED stopped blinking, but the pulse continues. So it's obviously using a hardware timer, which is good. That's better than it being a software timer, especially one in Python.
I wonder, 16-bit number. The example says duty times duty, and duty goes up to 255. So I don't know, 32767. Would that give us? Yeah, it does. Okay, there you go. Interesting. So it's basically a 16-bit number division between the frequency. Okay. Because if it's 20 millisecond divisions, we take 65536, and then we multiply it by, well, no, it'd be by times 0.1. 65535, and then we would add up to 3000 from that. Some of you are probably just like grimacing in the comments below. Okay, that got us a 2 millisecond pulse, so I think we're in the right ballpark. Maybe you're not in the right sport. 553, which is 65536 divided by 10, obviously. Then we divide that by 2, which gives us that. Okay, 3276. 3276. I guess it is, you know, you can just click upload and boom, it instantly updates. I mean, that's cool. Okay, there we got our pulse. All right, yeah, all right, so, okay, let's do this. Let's go back over here. Let's define set X servo. And that's going to be angle, colon. All right, so we're going to take... Oh, gosh. Sorry, math is not my strong suit. Okay, we're going to take 100. Okay, so it's going to be 18 ticks per degree. All right, so angle equals angle times 18 ticks. Okay. Then angle equals angle plus the base tick thing. I don't like these spaces. See, look how lazy I am. Programming is all about laziness, you know? All right, so if we set an angle of 90, that should give us a 1.5 millisecond pulse width, assuming it works. Looks like I borked it. I'll have to try again. Or maybe I forgot to call the function. Oh dear. It's the amazing Ben Heckendorn. He can do anything apparently. He could even keep the ones he loved from dying. Is it possible to learn this power? Not on YouTube. All right, so it goes 1 millisecond, 90 degrees is at the center. So cool, that should allow us to control servos. I think I'm going to use a random GPIO as an ADC to feed the random number generator. Let's see, reading equals, well, they have a sensor temp, so it would be .read U16 of the ADC. I wonder how many bits it is. Oh, it doesn't really matter because I'm just going to use it to feed. Well, I have to write the whole code. So it's going to be ADC. Oh, actually, well, no, let's just create a function. I'll call it def seed Okay, so ADC. Let's see. Cedar equals ADC read underscore U16. Is that? Oh, what if that means MicroPython 16-bit value? Then over here, actually, this is the BBC microbit Python, but whatever. Random range. Okay, so how do we seed? Random seed and then a number. Okay, so random seed cedar. Well, I guess we could have just combined that, but whatever. Seed so. That's such a stupid name. Yeah, well, okay, I'm trying to think. Okay, let's get... Okay, so we sow the seeds. We sow the seeds of discontent. And so let's get x equals random range. Let's be conservative. Let's only do like 40 degrees. And then, well, at least I don't have to... Oh, man, I'm having to type all this in? This goes against everything I stand for. Everything should be copy-pasted. Okay, so if that's 40, if we want to have it to be in the middle, that would be 90 minus 20. So that would be, we would do 70 plus x, 70 plus y. All right, let's see if that works. Ah, it is moving, although it's very ginger. It's a ginger kid. Oh yeah, also on the y-axis, we don't want to go above... well, we probably don't even want to go above 90, because if this is sitting on a table, you know, it's going to be shining the light, and the cat won't be able to get it. Yeah, so maybe I'll make the Y from, like, I don't know, like 100 to 180. Okay, I created a little routine here. So we sow the seeds, then we get the two ranges, we set the servos, then we get a random number for X again, clear Y, set A to 0. Then we blink the lasers a random number of times. Then we make sure the laser's on. Then we sleep for 1 second, and then we do it all over again. And yeah, it seems to be working out pretty well. I think I'll set this like on my kitchen counter, and we'll see how Big Fat Bud reacts to it. Okay, I've got it hooked up in my kitchen. The cat is dragging on the tripod. Let's test it out. Bud, I've created a new device so I never have to play with you again. What do you think about that? All right, here we go. It's too fast for you, Bud. Where is it? I can hear a little crunchy on that one extremity, so I'll probably have to limit it. It depends on your servo.
A lot of times you can't actually go from 0 to 180. Sometimes you'll, you know, all servos are different. Yeah, I think I should, yeah, watch the X extremity and then also randomize the speed at which it moves. Basically slow it down. So to do that, I'll just have to have have two variables, X and Y, and then it will change them incrementally towards the new value. That way it's not instantaneous. Because right now the servo's changing position at full speed. See, he's not even having enough time to pounce like a lion. Okay, I've got it varying its speed, variable speed. It doesn't do ramping, but it will move at different speeds. Although I think that might still be a little on the fast side. Actually, that move wasn't too bad. You gonna move the Y at all? Come on. There we go. Oh, it also varies how long until it moves, so it stays there from 1 to 3 seconds. See, that time it tricked him. One thing I noticed, well, obviously cats are meant to hunt, but like when I play with the laser pointer with him, myself in the kitchen, his periphery, it isn't very good. He, you know, well, I suppose it's, well, again, his eyes are in the front of his head. That's the way he was evolved or designed or whatever you believe in. You know, so if the laser's any bit to the side of him, he can't figure out where it is. Too slow. So yeah, the C setup was fairly obtuse. But you know, programming, again, I've never programmed in Python before. So, you know, it's slow, but it's pretty easy to do, and then you can just, you know, click the button and immediately update it. So it really is kind of like the new basic. I don't know if it's entirely appropriate for microcontrollers because, you know, it's one thing to put Python on like a, you know, a Raspberry Pi or your web server where you've got all these resources. But, you know, interpreted languages on a microcontroller, even at 133 megahertz, it's gonna suffer. My original, well, I'm still gonna do it eventually, but this is a 1950s house, so there's a wall clock outlet in the kitchen. And when I redid the kitchen, I couldn't remove it because you can't have buried wire termination. So I just put a new outlet on it. But the idea is eventually I'm going to have an ESP8266 module driving this thing, and I'll actually just attach it up there where the clock is, and it'll shine over the whole kitchen. And that way I can have it on a schedule, and I can also you know, activate it using the NSA Pringles can, as I like to call it, because I know people don't like it when I invoke her name on a video, because then everyone's own personal NSA Pringles can reacts. So there you go. That was my initial impressions and setup of the Raspberry Pi Pico. Yeah, I think it's most appropriate for like Python or MicroPython development. Yeah, that's pretty easy to use. As an embedded microcontroller being programmed in C or C++, it seemed like the tool chain was a bit convoluted, especially compared to something like, well, I like to use Atmel. Yeah, but, you know, obviously there'll be more libraries in the future. I think they really need to get this thing in Arduino, though. Because even though Arduino is like a big 400 megabyte plus folder of gobbledygook, at least you can just put it on your computer and it just works. You know, you don't have to install like 5 different tool chains just to program in C. All right, well, we'll see you in the next video. And yeah, if you like Python, maybe try the Pi. Bud, are you getting tired? Maybe I could keep Bud calmed down by making him tired instead of what most people do, which is to feed their cats and make them lazy and fat.